Another month, another topic from the handbook. So, if you don't know, I actually have my degree from the physics astronomy program here at Western, and most of it was the astronomy. So I do geek out, as my wife looked at me and just go nerd yourself out for a while as I'm going through this. And I do like sort of the more technical stuff here. As I see you, Caitlin, here, I can think you imagine you like that stuff too. So this month, no, not green.
Is that the green light on the side?
Yeah.
Click on. There's an funny on-off switch on the side. So when you turn
No,
on
it's gone back. Yeah.
next to dongle, they do a little handshake and then they're good to go.
Mine's instant.
This one isn't. I have that one. I speak from experience.
Okay.
Sometimes it takes more than one try. It's a cheap one.
No, I have the same one.
Oh, you have the same one. Mine's not bad. Mine's not that great. It works. I would unplug the dongle on the same playback.
Or
that makes it. Or do you go up and down arrows?
down arrow is not working either.
Good. Maybe you got clicked off. Maybe your palm is.
There we go. Oh, yeah, we've clicked off.
You run. So
Yeah, we were clicked off. So this month, looking at orbital elements, and I thought this might be apropos since we just all watched Artemis and we saw all the orbit for the Artemis as it was being updated constantly. And unfortunately, we saw a lot of, oh, they didn't actually go, but yes, they did. So page 23 from the handbook is a table for all of the orbital elements for the solar system. And I've just grabbed the planets, but they also have all the major asteroids and minor planets and everything as well. So it's all there. One thing to note is right there. Notice Julian dates, last month's topic. So all of the data there is set for 2 times throughout the year. That's the reason for there being 2 lines for each one. It's being updated twice a year. And the orbital elements then are by the column. So the 6 orbital elements that are there, mean distance, so that's a statement of the semi-major axis of the elliptical orbit, the eccentricity, inclination, longitude of the ascending node, longitude of the perihelion, and then mean longitude. So now I'm going to go into a bit more there. So of course, we all know that orbits are not circular, they are ellipses. So it's a geometric shape where the 2 foci, what would have been the center of the circle, have essentially been pulled apart. And probably easier to see, use the methods. So the semi-major axis is along here, whereas this is the semi-minor axis. And in the solar system, the sun itself is always at one of those foci points. And the eccentricity then, here's the geeking out part, there's a nice formula. So the eccentricity, E, is equal to the square root of 1 minus the semi-major divided by the semi-minor divided by the semi-major axis squared. So a little bit of geeking there. The inclination of the orbit is how tipped it is from a reference point. So the solar system itself, all orbits are from a reference plane. And in the case of the solar system, that reference plane is Earth's orbital plane. So what we call the ecliptic. And when you observe the planets in the night sky, that's the reason why they don't follow an exact path, why there's a band where the planets are, because we can see that inclination as the various planets go above and below the actual ecliptic. The longitude then, The vernal equinox, where we actually look at on the vernal equinox, is our standard spot. So we measure all the degrees from that point in Earth's orbit. So how far around from our vernal equinox is the ascending node? And the key here is it's the ascending, which means it's going up. And of course, is there up or down? From our vantage point, we call it from south to north. So as we're observing, if the planet is going from the southern hemisphere to the northern, that's the ascending node, where it crosses our plane. So how many degrees around our orbit is that point in the sky? Then the longitude of their perihelion. So where in their orbit is the closest point? And again, we measure it from our from the vernal equinox. And sorry, I couldn't find an image for this one. This just didn't work. Then to sum it all up, there it is. So you can see, oops. So the gray then is the ecliptic. That's our standard plane. The reference point, so that would be pointing to the vernal equinox. You've got the inclination of the orbit in question, how tipped it is, and then the measure to the perihelion and where the body is in its orbit. Now, just geeking out a bit here, I'm going back to the table, and I've circled one thing of note. So it's for Earth, and it's the inclination data. Remember I said that our reference plane is the ecliptic. So that should be 0, but it's not. Any guesses as to why it's not 0? You had a guess. Nope. Well, wobble is, you're on the right track.
Do they define that vernal equinox at particular?
No, it has nothing to do with the vernal equinox. They actually define the ecliptic by the barycenter of the Earth-Moon orbit. So as the two of them, as the Earth and Moon go around each other, they're going around a common center of mass. That's why there's a slight inclination here for Earth's orbit. And I just found that really cool because I expected that to be 0. And I had to know why. So there's my talk for the month. Back